All right. Good morning, folks. My name is Rob Gorham. I'm the Executive Director of the SecureAmerica Institute, and it is a pleasure to have Dr. Ankit Sharan with us today to talk about the curious case of copper and nickel alloys in additive manufacturing. The SecureAmerica Institute has been around for over a year now. We're part of the Texas A&M Engineering Experiment Station, and we're all about trying to advance manufacturing, resiliency, and security across a wide range of different manufacturing disciplines. We talk a lot about inside the Institute, artificial intelligence, additive manufacturing, the industrial Internet of Things, cybersecurity, and the list goes on and on. And today we're going to focus specifically on additive manufacturing, and we're very happy to have Ankit here to talk about a true passion of his. And one thing that I love about Ankit is he's an expert in systems, material, and process research and development. And so he understands the entirety of the additive manufacturing process. He also has a passion for accelerating engineering application. And I've seen him give several talks, and I'm always excited about his ability to relate his desire to accelerate the digital age of manufacturing to the 3D printing opportunities that lie ahead for us. He also, before working at EOS, was at the National, let's see, I can't remember the name of it, Ankit. You'll have to tell me. The National Aerospace Laboratory, I believe. And he's also involved in SAE. He spends a lot of time working on standards development, which we're very appreciative of, because as everybody who works in standards knows, that's a volunteer opportunity for all of us to try to make additive manufacturing successful. He holds a doctorate in mechanical engineering and a master's degree in aerospace engineering from the University of Illinois at Urbana-Champaign. And he's got a bachelor's degree in aeronautical engineering from Ann University in Chennai, India. So Dr. Ankit Sharan, I'm going to turn it over to you. And when we get done with this, just for everybody that's listening, either now live or via our online presence, we will be doing questions and answers. If you're not with us today in person and you do have a question, you can always reach out to us. You can find our contact information at www.secureamerica.us. Again, that's www.secureamerica.us. Feel free to put an inquiry into that website, and we will do our best to get back to you as soon as possible. Ankit, over to you.
Thanks, Rob. I hope everyone can hear me. Okay. And thanks for the introduction, Rob. I didn't know about all the stuff that I've done until you just told me. But I'm really here. Hello, everyone. I'm really here to talk about additive manufacturing and a specific thing on materials, specifically copper and nickel alloys. I can easily spend more than a week, but I'll try to condense it in about 30 or 45 minutes to give you guys an idea what the state of the art is and how EOS looks at materials, because I truly believe, the materials are the actual topic or actual principle that are actually driving applications in this digital age of manufacturing. So without further ado, just taking a look at all the different technologies we have in additive side for the metals. You do have a metal binder jetting, essentially also a powder-based process, but it's which is very fast, but it's kind of traditionally based into sintering and debinding sort of technologies. Then you have the directed energy deposition, which is for much larger parts. You might have seen videos of people making a huge oxygen and fuel cylinders directly out of directed energy deposition. So that technology definitely has its niche. Then we, of course, have on the powder bed side, the more two popular ones. The first one being the electron beam powder bed fusion, which is kind of a hot application where you're kind of raising temperatures almost up to an 800 C to actually build parts. So less stresses and faster deposition rates, but you're kind of suffering with surface roughness issues, and also in regards to the amount of materials that you can do. Essentially, then, of course, the more popular one is the direct metal laser melting, or also the ASTM term known for that is laser powder bed fusion, is essentially basically laying down thin layers of powder and kind of fusing and melting selected areas of the powder bed with a laser source. What I essentially want to say is that all four technologies are equal in their own right. It's not good, even though it's compared here, but in my personal opinion, I don't think it's fair that, you should compare them one to one. It's kind of comparing apples and oranges. It kind of drives, depending on what applications you have, it's kind of drive or determine your choice of application. So please don't pay attention to, or do pay some attention to all the marketing stuff out there, but really take a look at the application and see what technology fits here. But anyway, talking about laser powder bed fusion, if you guys are not familiar, if I had to explain it very, very rudimentarily, it's basically really kind of transforming your ideas, what you have in your hand, to basically actual parts in your hand. I had to explain this to my kid a few weeks ago, and kind of what I use is a very simple analogy. It's kind of basically making parts with light, in this case laser, and of course sand, which you can call material powder, and of course thin air. It's not exactly thin air, but you have shielding gases, argon or nitrogen, and what you would get is basically a part like that. So here's a part what I appropriately took for the topic of presentation today is a copper chromium zirconium combustion chamber. And I'm going to talk about the company here a little bit to see how this part came into being and what the challenges were and how we kind of went from there. But the number one topic that always comes out is, and I'm being asked this frequently, and you guys might wonder, is what is the state of the art? Or if this is the state of the art, what does the future of this technology hold? And if you look at that, the question is not that trivial, in the sense that the future kind of depends what the applications are going to bring. And you can look at the future both from the hardware side of things, where you're talking about new light engines and faster lasers and multiple lasers. You might have seen a couple of them kind of getting announced recently. But essentially what I'm trying to focus here is still the materials. What does the future hold in terms of materials? Because that's what's going to drive the hardware requirements as we move forward. So if we're just talking about materials and processes, we of course have high strength alloys. I call them the flavor of the season. I see every new aluminum alloy kind of coming up every 3 to 4 months for additive processes, but it's definitely something that the industry needs. Then, of course, we have metal matrix composites kind of driving the industry from there on and kind of offering new material choices to designers to design parts for. Of course, you have lightweight alloys. Again, lightweighting kind of imagining not only from topology optimization of the parts themselves, but also kind of looking at new chemical formulations by which you can maybe even somehow reduce the aluminum alloy densities, for example, from let's say 2.67, which is a traditional silicon 10 mag, to maybe let's say 2.4, 2.5. So definitely watch out for this space. Then, of course, you have functional alloys where you're talking about more microstructure control, where you're talking about alloys which are more meant to function. For example, in this case, would be a shape memory alloys like nickel titanium, for example. I think this is what the future ahead holds. But just talking in terms of copper and nickels, it's a huge new area that's just opening up. Nickel's been around for some time, but coppers are a little bit brand new. So we'll talk about that as we move. But what I really want to say that when the industry actually started, the two main technology adopters in the additive industry were aerospace and medical. I'm talking back in the early in the last decade. They were the main drivers of the technology, not only in terms of production, not only in terms of prototyping, but also in production, because they actually showed the path of how this technology can be a viable source of production. Now, fast forward a decade, now we see a lot of space companies, and I think that's where a lot of innovation is now happening, and that's where a lot of extremely new materials and extremely demanding applications are coming to the fore, where people are now demanding more higher temperature parts, more oxidation resistance parts, more higher performance, higher pressures, and everything. And the reason why this is happening is kind of a boom, what we call the space boom. Like it's, you can see here, there are a number of launch vehicle companies actually everywhere in the world, several of them located in the US. But you can actually see from 2015 to 2018, the worldwide launch in terms of low Earth orbit vehicles, which is a pretty a lucrative market these days, it's kind of grown quite significantly. But when we talk about rocket side or space side of things, the technology innovation was there, but it was mainly on the federally funded side, where it was a NASA and a few national labs kind of driving the innovation until SpaceX and the Blue Origins of the world came to the scene, where kind of, if you see on the left side, this is an Inconel rocket chamber with a regenerative cooling design that was printed in Inconel 718 back in 2013. So that was almost 8 years ago. It kind of seems like yesterday, but you can see how technology had made progress from then until now, where it was unthinkable more than 15 years ago, 18 years ago, to maybe, land a rocket back in it and, reuse it to drive the cost down. And now it's like, it's expected that every new launch vehicle that gets launched, the reuse part of it is now a basic benchmark, and you need to be able to have this. So that's why I think the technology has even driven the bar for performance much higher and kind of helps the world across. And then, of course, you have the Rocket Lab. It was the first battery powered rocket engine, and it was entirely as well 3D printed. And you can see that these applications kind of do demand a lot more materials, a lot more challenging materials to be done, because it started all within canals and 718s and 625s, but it's now quickly gone into, hey, I need copper, and I need copper to withstand not only high temperatures, but high pressure in these vehicles. So how we look at these technologies is basically a technology readiness level. So people familiar with this is the term that NASA came up with to describe how technology advances from the lab all the way to the launch stage where it's ready for production. And it's what we call the technology readiness levels, rating from 1 to 9. So when we talk about an EOS technology readiness levels, we've kind of taken the guidance and, kind of getting inspired from NASA TRL levels, and we've kind of established our material TRL levels on the same levels to what NASA describes, in a sense that helps customer understands what the maturity of the technology is and how efficiently and what can you expect in terms of promise from these materials and processes. So if I lay this all down, and from TRL 1 to 9, we kind of bucket them from TRL 1 to 3, where you're initially just talking about, hey, can I make this part? Can I process this powder in the machine? Is the part weldable? And even to that case, the first one is, can I even make the powder for this alloy, which a lot of people take for granted, but it's not that easy. Like, atomization is its own science, and it's its own field in itself, and it's pretty complicated. And not every alloy that you see can be atomized as well. So there are challenges definitely with that as well. And of course, since we are in a commercial company, we're not in academia, we of course assess the business case. Like, if we are able to print the material, doesn't mean it would see the light of the day, as long as, if the part is printing too slow, or the process is just wrought with too many post-processing steps, that it just kills the business case at the end. Then, of course, is what we come with design freeze and validation, where we're kind of really optimizing the part properties, kind of testing various heat treatments that come with the parts. Additive essentially is a cold process where you involve rapid heating and cooling of thin layers of powder, which induces a lot of stress in the parts. So like any other process in a metal processing side, you would expect to do a stress relief procedure and an aging treatment afterwards, depending on the alloy you're working with. So a lot of heat treatment optimizations are done in this phase. And of course, we generate initial mechanical data coming out of it. And hopefully at the end of this stage is somewhat what we freeze the process in terms of parameters, in terms of post-processing steps, in terms of powder specifications. And of course, the 7, 8, and 9, what we talk about is standard data, what EOS is typically known for, high quality materials. We're talking about data sheets coming out, fatigue testing and dynamic testing data coming out, where those tests are typically expensive, so we kind of reserve them for higher TRL levels, where design and material levels need to be generated, and of course quality assurance testing needs to be established at that level. So now we talk about new materials, and we see that we can do a benchmark across this chain. All the way as in the early materials, we can show the promise of what the materials can do to somewhat what we call as a custom solution. If it's a we've done a lot of projects with different companies where the chemistry is really proprietary for that specific company, and we kind of create a custom solution by making a process ready for that specific application. And of course, we have the standard solution across all TRL 1 to 9 levels. So it's very important to understand what the TRL levels are when you're talking about materials and processes and how they impact your qualification down the road. So we've talked about EOS, TRL level, but of course, when we talk about customer manufacturing readiness levels, they don't match one-on-one. Just because we have a material that can be processed doesn't mean that you can just take the material in and just make an end-use part, throw in a rocket or throw it anywhere and expect it to work. Of course, you would need to do some work on your side, and that's where a lot of help comes in terms of design and in terms of support strategies, in just terms of process simulations that need to be done to make the part work. And that's where we kind of make the distinction. And we, of course, are in no way under the assumption that, hey, if a TRL 456 doesn't mean that, manufacturing readiness level isn't that high. It's manufacturing readiness level always kind of follows behind our TRL levels. And to assist that, to bring your manufacturing readiness levels up the game, we do help through our additive minds team within EOS, where we kind of help you understand the process and help you drive applications. Now, just talking about alloys today, all known alloys, you're going to imagine there could be about more than 1,000 easily. Talking casting, forgings, all different kinds of brazing alloys. And on a casting alloy is about 700 alloys. And if you just talk about additive, and I'm talking just about EOS materials themselves, what's on offer was about 16 materials. That was about roughly 3 or 4 years ago. So you can imagine it was a tiny dot in this whole thing, which you can't even see. So as you can imagine, there's an immense potential in terms of materials that can be offered as part of this technology. So when we take a look at materials, here are the prime materials that are available in any additive manufacturing technology today, as far as laser powder bed fusion is concerned. You have aluminum, cobalt chromes, nickel alloys, tool steels, stainless steels, engineering steels, titanium, refractories, and of course, copper. Refractories, copper are turning out to be more attractive, especially from the federal government after the hypersonic initiative. They're coming more and more to the light, and a need for, of course, higher a lot of research funding going into actually making some of these new chemistries involving some novel materials like hafnium and other stuff to a reality. But we can, like I said, I can talk about materials months and months on end. I won't have any issue, but right now we're just focusing on nickels and coppers, so we'll just keep an eye on that. So talking about copper, on what copper is. So the number one driver from the copper, which is kind of driving performance, is conductivity. And what we mean by conductivity is what we call an ISES. So ISES basically stands for International Annealed Copper Standard. To what basically means is what you would expect for an annealed copper and what would be the conductivity for that material. That's what's taken as a gold standard, and every material that you see is kind of held against that. So you start with, on the left-hand side, where I'm talking about steels and iron, we're talking about, very low, less than 20% conductivity. So you can actually imagine that these materials are not suitable for high conductivity applications, to where we're talking about aluminum and even pure aluminum, where you're about just between 45 to 65%. So traditionally, a lot of high conductivity applications used aluminum silicon 10 mag, but you're just talking just less than, just right about 50% ISES values, which was enough at that time. But again, this is something that is coming, it quickly became a very limiting factor in how applications are kind of coming to additive side. Fast forward today, now we've got copper and different copper alloys. You're talking about pure copper, and even pure copper, you're talking about two grades of pure copper, which I'm going to talk about, which almost go up to almost 100% ISES, which means that you can imagine a full conductivity performance that you would expect from a pure copper. And of course, copper alloys, which are again very popular with the rocket industry, where they're kind of alloyed with hardening components like chromium and zirconium just to add strength. So they are not only able to conduct heat at a higher ratio, but they're also able to withstand pressures that are coming with such demanding applications. Now, just looking at pure copper. So this is, I'm talking about a 100% pure copper. And if you're talking about purity, you're talking about more than 99.95% pure copper. It's an excellent thermal conductivity. It's mainly used for heat exchanger applications, and you can achieve pretty good surface finish from sandblasting and other post-processing techniques. We've got a huge new applications projects going on right now where we're not only processing pure copper at near 100% density, but we're talking about thin walls. And how thin we're talking? We're talking about 150 to 180 micron thin walls, which cannot be manufactured in any other way rather than additive. And these are the applications which are going to drive the copper demands, especially in the semiconductor industry or the electronics and consumer electronics industry when I talk about. So, and what you would expect from a material, you open it up, it's like I said, this is an example microstructure here, it's nearly completely dense. We're not talking about 94% dense or 93% dense. We are talking about almost 100% dense copper. So that's what the part performance is in terms of microstructure. And of course, when you do a heat treatment, you can expect a moderate heat treatment effect. And in terms of electrical conductivity, we've seen that you can almost achieve up to 100% ISES values in terms of performance, which is, the prime criteria for down selecting some of these alloys. So this is copper alloy, which I'm talking about is a pure copper alloy. Now, second one we're talking about is another copper. It's another pure copper, sorry, not alloy, I apologize. Another pure copper, but now we're talking about 99.7%. And people who are dealing with copper, they would know the difference that 99.7% and 99.95% pure copper makes a huge difference in terms of what potential processability issues you might have. The reason we've got a 99.7% pure copper is because the last one can only require, just because of a high conductivity, the material it kind of acts as a big heat sink and kind of deliberately outgasses a lot of heat while in the melting process. And because of that, you need a lot of juice in the laser itself to be able to process the materials at that high density. And you require a 1 kilowatt laser to be able to do that. But however, as we know, and many of you might know, that from EOS side in terms of field, a lot of people have an M290, which is not equipped with a kilowatt laser, but is equipped with a 400 watt laser. So to deal with that issue, we kind of came up with a 99.7% pure copper, which you can actually very good for, again, for thermal conductivity. You can get almost very near to ISES values and also can get quite good surface finish. However, in terms of porosity wise, you're still talking about 95% porosity, which is essentially the result of a lower power laser here. And like I said, in terms of conductivity ratios, you can almost get up to 90%. So if that's your prime driver and the cost wise, this still seems like a good application. Now, the last one, of course, is copper chromium zirconium. So this is something that I said before is not only in terms of conductivity wise, but also presents a very high strength. It's also known as CU1850 and is very closely in resemblance to performance with GR-COF42. The prime difference between GR-COF42 and this being basically the cost, where the GR-COF42 could be about 3 or 4 times as expensive as copper chromium zirconium. But if we talk about the microstructure, it's almost 99.5% dense, pretty high strength with, again, very comparable heat conductivity values, which is, like I said, very, very popular with the rocket industry. And when you actually do it with 80 micron layer thicknesses, it's highly productive as well. So when we talk about possibilities with copper alloys, this is not the end. There's a huge copper alloy possibilities that you can actually see. We've got brass-like materials. We, of course, have copper nickel-like materials that we're working on right now. And of course, as you can see, there's a lot of unexplored space, which is going to result in a lot of newer applications that are just waiting for us to explore. This is just the state of the industry today. And like I wanted to say that copper, what you might hear, is actually more mature than what most people actually perceive to be, where you actually see a lot of literature in the market claiming that, okay, they'd be possible to do copper, and they finally made copper done possible. We've been doing copper since almost 4 years now. So now moving on to nickel superalloys. So when we talk about nickel superalloys, we're talking about gamma fraction, gamma prime fraction, which is kind of prime driver of strength. And of course, I've kind of plotted different alloys in the gamma prime fraction, and of course, a maximum service temperature that you can expect from these materials. Sorry. Now, you've got the traditional materials. You've got 718, 625, and HX. 625 and HX have no gamma prime fraction, which kind of, they're not as high strength, but they've got much higher maximum service temperature. But if I'm looking at 718, which is not essentially a gamma prime, but it's a gamma double prime, and it's got a lower maximum service temperature, but much higher strength than 625 and HX. If you look at the space, Inconel 939 is just what came up, and we just kind of released this material as well. And of course, you have the traditional alloys, the Haynes 282, the 738, and of course, the holy grail in nickel superalloys, what we call is the Mars M247. And of course, you have other alloys, Ren 80, GDT 111, and basically, these are what you would characterize as your vein alloys, and these are what you would characterize as your blade alloys. And as a whole, all these alloys are basically hard to weld. That means that from a physical or from a thermodynamic point of view, they're not easy to weld, and hence kind of a challenge doing that using additive. However, with the recent advances in technology, we've been able to launch Inconel 939, and I'm happy to share some information on Inconel 738 as well today on the presentation. And of course, if I'm talking about other alloys, you of course have 242 and Haynes 230. So as you can see, even on the nickel superalloy side, the market is far wide open. So when we're talking about Haynes 282, let's take the first one. Everyone knows about 718, 625, and HX. I'm not going to waste time on that. But if I'm just talking about the newer alloys, let's talk about Haynes 282. So this is a microstructure we've been able to achieve, and the material is fairly easily weldable, very easily comparable to 718. And it can be done in both 40, 60, and 80 micron layer thicknesses, driving the innovation, driving the production from that standpoint. And the mechanical testing at room temperature do meet standard requirements from the 5951A as well. The high temperature testing actually showed very close performance to the rod side. And of course, creep testing also met 5951 on the horizontal, on the vertical side, but on the horizontal side, it was quite close. And I just want to share some results here as well. So when talking about Haynes 282 in the room temperature testing, here's the plot. So this pink bar here is for cast. So this is a cast for a yield. So the pink one is yield, the blue ones are the ultimate, and the green ones are basically your elongation. So if I'm talking about casting values, this is the bar for yield strength for casting. And as you can see, we easily beat that. And if I'm talking in terms of UTS, we kind of in a heat treated condition, we also beat that as well. And if you're talking about elongation, of course, that just means that Haynes 282 can meet casting requirements any time of the day. Now, when we're compared to forgings, which are much higher performance, now we're comparing with plates. And as you can see, we're quite close in a heat treated condition, but not quite there yet. But still, I would say we're about 95% of the way. And like I said, I'm personally very happy with that it opens up a lot of applications and just shows that it's almost meeting forging requirement specifications for Haynes 282. Now, talking about the stress rupture testing, this is a graph that's basically taken from literature, And as you can see from the vertical side, we are almost there. We're kind of there and we kind of surpass it. But on the horizontal side, we're very close, but not quite there yet. So even from a stress rupturing side, that's what we've kind of found, that Haynes 282 from an additive side is very, very viable alloy. Now, one thing I also want to say that for nickel superalloys, it's not always about fatigue. It's sometimes about stress rupture, sometimes about creep. Again, depends on what the application of the alloy is. So please pay attention to what data you have out there, what the allowables are, and what the maturity of the allowables are as well, to be able to understand what the performance of a specific alloy is going to be that is manufactured additively. Now, talking about Haynes 230, this is another alloy that is very comparable to Hastelloy, but actually has a much higher service temperature as compared. If you see on the earlier plots, it kind of surpasses the oxidation resistance to almost 1100 to 1200 C, which is far higher than what you would expect from Hastelloy. And as you can see, this material as well is possible in additive, and the conditions that we get in terms of mechanical strength are very, very comparable to what you would expect from a casting side. Moving on to 939. When I'm talking about TRL levels, this is a material that we have a very high TRL level. We have very high confidence in it. And this material is getting deployed more and more into the industry. This is only about a little over a year old and provides excellent fatigue and creep resistance strengths at high temperatures, and is mainly intended for gas turbine industry, for some turbo machinery, and some process engineering in the chemical side, where they kind of provide a lot of strength and a lot of oxidation resistance as well. So it's not only the mechanical data that, like I said, in this case, high temperature tensile testing also matters. So you can actually see that the material is almost pretty stable, almost up to a 600 Celsius, which is about 1100 Fahrenheit, before it drops in strength and kind of goes from there. So now talking about 738. Now 738, if people know, and if you've actually seen some literatures, you can do 738 LC. LC basically is low carbon, but if you can do 738 in an additive environment, no problem. But when you heat treat it, you actually suffer from solidification cracking. And what these solidification cracking are, like you would have this microstructure and you would not be able to see any cracks, but when you do a heat treatment, you would see some of these cracks pop up, and these are solidification cracking that are resulting because of the heat treatment process. And what we've done is we modified the 738 chemistry slightly a bit. It kind of drives the chemistry a little outside the bounds of traditional 738, but the resulting microstructure is crack-free. In that sense, what I want to say is that not every conventional alloy can be done in additively, but you can have existing alloys modified that are meant for the additive process that are not only going to be defect-free, but can also drive performance much higher. So in terms of performance, here we're talking about high temperature tensile properties, and you can actually see we are at much, much higher levels. And the properties all across the board look pretty good in terms of high temperature tensile testing. And the material seems, at least on a lower tier level, what we've shown at about 3, or I would say about 4 or 5, that we've shown the material to be an excellent viable candidate for a traditional 738 replacement. But we're talking about the future, so let's look at the day. What about 100 alloys, casting alloy 700, and I want to say is that from an EOS perspective, just what we've talked about in the last 2 years, we've gone from more than 16 to 34. In just 2 years, we more than double the amount of alloys. And this is something that just EOS has done. There are a lot of other companies out there, a lot of other, like for metrics, like NanoAl, like Elementum 3D, like other Castilian, AppWorks, like Scamaloy, all these other companies, Oxman, Alloyd, all these companies out there that are driving the innovation from the material side. And I can imagine, like right now, if I have to put a number, it would be about 100 materials that can be done in laser powder bed fusion today, much more than any other additive technology that is on the market, which basically shows that this is a much more mature technology and a much more penetration. Now, when we're talking about, again, future alloys, I just don't want to say just on copper and nickel. I just wanted to also show you a few highlights. Like I said, I can talk about materials all day long, but we're talking about magnesium alloys that can be done. We're talking about bronze alloys that can be done. We're talking about Invar, very high. It's a material that's used in satellite industry quite often because it's very, very low coefficient of thermal expansion. So it's a highly sought after material that can be, we've done this material as well. We can do improved surface finishes. We're talking about carbon nanotubes and improving the aluminum matrix strength by embedding carbon nanotubes. And we're talking of new kinds of aluminum. So very quickly, here's most of the additive aluminum kind of fall in the yield strength versus elongation ratio, where here's your silicon 10 mag, here's your silicon 10-3, here's your F3512 silicon mag, and I don't see a 7-1, but I can see 7 silicon mag is somewhere here. But what it actually shows is this space is quite empty. And that's where we see a new aluminum alloys coming up. We're kind of working on an internal aluminum alloy development that is going to put the aluminum alloy right here in this space. With a high strength, about 450 MPa, with much higher elongation, about 15% elongation. That is kind of not entirely unheard of, but it's kind of something that hopefully helps the customers drive the aluminum adoption in the industry as well. Now, we're just talking about materials, not just talking about hardware, just a little bit. So when we're talking about AMCM, and I initially talked about the space industry, so kind of pivoting back to that. Now, space industry needs huge parts. And what we're talking about laser powder bed fusion from an EOS side, or even from other perspective, you're kind of limited on size, but we have a sister company called AMCM, which essentially stands for Additive Manufacturing Custom Machines. And what a custom machine basically are famous for is basically building machines that are not standard, that fit for your application and are kind of made for what they're intended for. So here's an example of a machine that can go up to your 1 meter tall parts. So just to give an example, I'm not a commercial guy, so I'm just gonna very quickly tell you that the machine can almost go up to a 450 by 450 by 1 meter tall height. And just to show you the parts, this is an example of a part that came out. And the company I was referring here to was Launcher. And they initially started with a copper, chromium, zirconium, and now they're talking about copper, chromium, zirconium small parts, which the parts ended right about here. And they were talking about welding multiple parts together to make a full chamber. Now we're talking about making full chamber top to bottom in one piece. And that's kind of a game changer. That kind of removes a lot of processing steps, and that kind of helps the industry drive more applications, more materials, more demanding, and kind of help additive technology push a lot harder. Now, when I was talking about rocket side, the holy grail right now is the bimetallic alloys. Now, additive is not traditionally known for bimetallic alloys, but what this company did, I'm talking about Launcher, they built this part. This is a copper, chromium, zirconium part, essentially. So it can withstand high temperatures, can conduct heat. It can withstand probably high pressures, but not at the pressures that they want. So in order to alleviate that problem, they kind of sprayed that with Inconel powder. So it's a thermal spray process. They did an Inconel powder coating, which helps with withstanding pressures, but at the same time keeping the high conductivity, which you would expect from copper alloys. And what now happens is with this regenerative cooling design, your chamber is actually a lot hotter than the melting point of this copper, chromium, zirconium. And the only way they're able to do that is with a regenerative cooling design where the fuel itself is cooling the whole part down, not letting the material or the nozzle melt on itself. And at the same time, the high pressure, this is what the Inconel spray coating is for, that kind of is able to withstand the high pressure. Traditionally, you would have done this process using brazing, but because of brazing, you would not be able to handle the thin wall features that you would traditionally go with additive. So this is what is now a game changer for the thing, because they can get much higher performance at much higher pressure of these nozzles. So With that, I just want to finish my presentation. There could be some questions. I threw a lot of information at you guys. So if you're confused, that's okay. You're not the only one. If there are any questions, I'm more than happy to help. But yeah, that's it from my side. Thank you.
Ankit, thank you so much. This is really great. It's super exciting too. When I was fortunate enough to spend time at America Makes, it was always interesting to see these new materials come online. And I do have a question when you think about the future of materials, and certainly you showed EOS's materials relative to all of the alloys available. How do y'all go about actually prioritizing how fast and sort of in which order you bring these new materials into the market?
That's a great question, Rob. And the question, to be honest, we don't have a great answer to that. It kind of very much depends on what the market demand is. Essentially, that's a holy grail. Of course,
Yeah.
there's a technology push as well to understand, can this material be done or not, and what the challenges are. Because honestly, there's a very high demand for Mars M247. But the only reason we haven't brought it to the market is because it's pretty difficult to actually do. It's a very high technical challenge. So it kind of has to, fall into that sweet spot where this can be done technically, and also at the same time, there's a huge business demand. Initially, that sweet spot was very, very small, but now we're kind of expanding that sweet spot to much larger, either by doing alloy compositions differently or by making strides in technology itself.
Yeah, and then obviously with your role in the standards community, I mean, I remember there's a good friend of mine, John Barnes. He used to say, if you care about 3D printing, then you should feel obligated to be part of standards, and because sometimes it can be painful. The process is long and it requires consensus, and a lot of different people are involved. Where does standards fit in this whole journey of introducing these new materials? Do you see it as it's currently supportive, or it's currently an inhibitor to the ability to get these to market in a way that that matters to the people who need to see these things turn into reality?
I personally feel that standards are always supportive. They may not be able to catch up with the pace of innovation and the material that are getting released into the market, but they're definitely supportive. And I know when the SAE group started with EAMS standards, I'm talking back in 2017, 2016. At that point, GE Aviation already had a few laws allowed in production.
Yeah.
So it's always kind of a following game, and you have to keep in mind, like you said, it's a long process. You have to build consensus, and technology is not waiting for standards. It's going to keep on going. And I think as a standards community, I think we're kind of doing a much better job at kind of keeping up to date, but it's been a hard place. And what I also want to say is that we're talking about multi-laser technologies today. We're just able to cover, what's the state of the art today, barely able to cover standards wise. What I see in the future, 5 years from now, new light engines, we're talking about area printing, we're talking about volume printing. We have a lot of work to do on the standard side. And I kind of look forward from the industry participation as well to kind of help drive them to a conclusion and help adopting them.
So interesting. You said, you used the word 5 years. Where are we going in 10 years? And what applications are we going to get to start seeing in the next decade with some of these new alloys that are coming online?
So in 10 years from now, it's very difficult to say what additive is going to look like. Like if somebody asked me, 2015 onwards, what the additive is going to look like, it's so changed. A lot of new players on the market, a lot of new technologies on the market. What I personally feel from 10 years from now, I think right now a lot of alloy design is still based on, okay, can we mix what the chemistry outplays are, how can we mix these different alloys, and can we make these alloys? What I feel in the future, it's going to be artificial intelligence is going to drive a lot of these applications. It's going to drive a lot of material requirements together. And I personally also feel alloys that could only be made in space. That's my dream. I kind of personally feel that in the 60s and 70s, kind of NASA did some experiments up in space where they can actually, take very two very different alloys in terms of densities and kind of made an alloy, mix them together to make an alloy, because in Earth's gravity, they would segregate naturally. But if we are able to do that, that just is a brand new field. That opens up a whole new plethora of applications.
Ankit, I think you've got a show on Sci-Fi Channel. This sounds pretty dadgum cool.
Oh yeah, no, absolutely. I think we're living sort of this right out of a sci-fi movie sort of a thing. We're talking about reusable rockets. We're talking about new materials, new alloys, artificial intelligence, data packets. It's all exciting.
That's sweet. Hey, one of the things that's been really interesting over the last couple of years is looking at the critical minerals list that gets published by lots of different organizations. And certainly there's been a lot of discussion recently around, critical minerals and accessibility of those minerals and availability of those minerals. With copper starting to see its way onto some of these lists, do you think that maybe switching over production to additive has a benefit around preserving the demand for some of these materials, or do you think we're still going to see some of the existing challenges faced on these critical minerals lists?
I think we're still going to see some existing challenges with the existing mineral list, because that's how it is. I mean, there's no way around it, to be honest.
Yeah.
But what I do see is that what COVID has shown, in a way, kind of forced everyone, is to show that supply chains can be resilient, supply chains can be distributed, and now we're talking about we're recently working with another company that is now looking up to start a first titanium mining operations here in North America, where most of the titanium from the additive side is not going to come from Japan or Russia, from China. It's going to actually come from the United States. It's
Oh.
right out in Tennessee. And they're kind of doing it in a way that not only secures the supply chain from the United States perspective, from a defense perspective, from looking at securing the North United States supply for titanium, but also looking at it, doing it in terms of sustainably. So basically, taking the Kroll process that is traditionally used to make pure titanium out of titanium dioxide, because it's a very heavy carbon process, use a lot of waste, and it's not at all sustainable. Kind of throwing it out the window and kind of using basically a zero carbon process to reduce a titanium oxide into a pure titanium.
Wow. That that's exciting. Hey, do you guys at EOS, for all of those materials that you did show, do y'all have materials allowables for those? And do you develop those internally, or do you develop those in concert with customers?
So most of the Inconel alloys that I showed, I'm talking about 939, we do have allowables for them. Most of them are developed internally. But some of the copper alloys, just because they're early TRL levels, we don't have all the allowables ready with us, but we do work with our customers kind of generating them. We're also working with MMPDS and the Battelle Group, kind of helping what the test matrix need to look like, and try and see, can we supply them data to actually publish allowables. What I recently came to know is that the allowables from additives are not going to be called A or B bases. They're going to be called C and D bases. And
Interesting.
and the FAA and NASA and DoD are not going to take allowables like they do with other conventional ones, and just take it as they are. But they would require proof of these C and Ds allowable, just because how different the machines are, how different technologies are, and it depends a lot on how you qualify your process as well. But we
Yeah.
do have a lot of data on Inconel 939. We do have a lot of data on that. And we're happy to work with customers and helping realize, like I said, we might be on TRL9, but from a customer manufacturing level, readiness level, we just be at an MRL5 instead. So we will help bridge the gap with the customer, bringing up from MRL5 to truly an MRL7 or an 8, where it's truly ready for production.
That's cool. Well, I just got a couple more questions for you, and then we'll wrap this up. I do want to kind of circle back to something that you've already kind of hit on, and where else do we need to begin thinking that the future of additive is going to go in your mind? And you can speak just as a like a non-EOS guy, or you can speak on behalf of EOS. It doesn't really matter to me, but I would love for just a second you to use your imagination on just trying to help us get our head around the gravity of future additive applications with some of these really incredible alloys coming online.
Right. So I personally think that additive is coming out from a powder bed side. We're at a cusp of technology revolution, not an evolution, I would say. Laser optical engines, we've kind of utilized them maximum to the fourth. You see 8 lasers, 12 lasers, 4 lasers on the market. You can add so many lasers before the system starts becoming too complicated. Now we got to talk about how we kind of do optical light engines, where we can basically pixelate one beam into thousands of belt pulls on the powder bed to be able to do that. And what that would allow us to do is not only realize some of these hard to weld materials, but also allow us to do in situ alloying, where we are not talking about a Ti-64. For example, you can throw in basically a Ti-64 blended with specific constituents, and depending on your parameters, you kind of driving intermetallics depending on position-wise where you want them in the part.
That's cool.
Yeah, qualifying that, I don't know. It's going to be a nightmare, but from a standard perspective. But from a technology perspective, that's where I see, and that's where honestly I see even from a refractory standpoint, because I think refractories and high temperature materials are very, very crucial to the hypersonics program, and we haven't really even scratched the surface on refractories. We are just talking. We at EOS we've done tungsten, that is available. We've done moly, we've done rhenium, we've done zirconium, we've done tantalum. But when we start combining them together, like moly, rhenium, we're talking about tungsten, hafnium. That's where the change is going to happen. It's kind of very counterintuitive, for hypersonic programs. You want them to be light, but at the same time, refractories are not light. They're the opposite. They're very heavy.
Yeah, yeah.
Excellent thermal barriers, excellent thermal resistance at those high temperatures.
Yeah. Well, listen, Ankit, thank you so much. EOS has been a great friend of Texas A&M and the SecureAmerica Institute, and I know that y'all are doing some just incredible work. It's been an awesome chance to speak with you. Please, for those that do get a chance to listen to this after we put these online, make sure you follow and subscribe to the Twitter and LinkedIn pages. EOS is always putting out some really great content. If you're not subscribed to our content as well, you can find us at SAI_Ts on Twitter, or we also have a Facebook and LinkedIn page. Both of those can be found by just searching Secure America Institute or our SecureAmerica.us website. Ankit, thanks. Have a wonderful rest of the day. And for those of you that have a chance to join us, I look forward to catching up with y'all soon. See you later.
Thank you, Rob. I just want to say that I'm really happy, and it's a really privilege for the SAI to invite me for the meeting. And I hope for the audience that if I didn't answer any questions, I hope raised a few questions in your mind. So happy to answer them. I always try with my talks is not to answer them, but actually raise more questions.
That's right. All right. Thank you so much.
All right. Thank you.
Signing off. All right. Bye-bye.
Bye.